Good morning, Brittany. How are you?
I'm fine, Chair. Good morning.
Okay, so next week your class will start already lah. Online class.
No, the week after that.
Oh, we still got one more week. So how is your
Hmm.
progress in revision?
Yeah, slowly reading and doing exercises.
You need to do, after revising each topic, you need to do the focus question. That's the only way to go forward. Right? So far you have receipts of doing homework. That's why you are not progressing forward. Okay or
But
not?
even hard also just do that, Chair.
You try it out. Don't know, ask me. You must force yourself to try to understand the question. You don't know how to answer, you definitely will not know how to answer in the exam. That's most important. You fearful, you have to learn to understand. University, the same thing. Nobody is going to help you. Only you have to learn to get close to good student and then approach them nicely to get them to help you. Because there is no more tuition in university. So how
Good lecturer.
how successful in university will depend on your own discipline. Those who don't have discipline, don't have time to study, don't have time to do the homework, will not do well. Right? Because university, most likely you have coursework, assignment you have to do, tests you have to do, that contribute to part of your grade. Only in school you can get away with all these without coursework, except your practical. Okay. Anything you want to ask?
So far, no, Chair.
So far, no. Okay, let's go to our wave optics. You should be listening to the video and then go and do your homework. That's all I can say to you. I can't help you much unless you want to pay me to revise with you. Okay, we go to interference in thin film. Two more topics to go after this one. 23.4. Yeah, your page 168. Explain the phenomenon of thin film interference for normal incident, right? Key is normal incidents and solve related problem. Okay, the key to all this is remember this equation. Right? I hope you got your worksheet. This equation, which I have forced you to write it up, but if you don't want to learn, I can't do anything. Right? Can I complain to your mother? As your constructive interference, memorize that. M lambda. M start from 0, 1, 2. Right? Usually we are more interested in one only. Then destructive is 2m minus 1, close bracket, half lambda, or m minus half lambda. Okay. M minus half lambda also can. Right? This one start from 1, 2, 3, destructive interference. You can't memorize all the equation because there's too many. Just memorize the basic one. This one, memorize that, memorize that. Okay, we'll be using that throughout. Let's go. Okay, that's the effect of thin film interference. Right? Bubble. So bubble, thin film interference. This one also a photoshop of a draining soap film and the color produced by constructive and destructive interference. We will try to explain to you why it got all this color. Right? So example of thin film would be color seen reflected from soap bubble or thin film or oil on the surface of water. Even on road there, sometimes people drop oil. Right? If you look at certain angle, you can see the color there on the oil film. This is a result of interference between light reflected from the upper and lower surface of the film. Okay, as I say, you can get from internet. Remember that this is a diagram. It's not a true picture. True picture means these two are very close together. And we are not interested in an angle. Right? We make this angle very small. By right is normal incident. Right? Directly down there. But normal incident will be difficult to explain to you. Right? Keep that in mind. This angle is very small. So this angle is very small. So it is actually vertical. If you want all these unnecessary calculation. Right? At 180 degrees phase change on reflection at this part there. Right? Occur when light incident from a less dense, this is a less dense air. Right? This is your thin film, a film. N is always greater than 1. This is a denser medium. Reflect off a boundary with more dense medium. Right? So at this part, there's a phase change of 180 degrees. Of course, this diagram is a bit poor. This one should be half only, not 1.5. Okay, so just forget about it. Just think of this is half. Right? That one is where we start. The interference will be, the path difference will be the same. Okay, sometimes we draw it as a triangle. Show the extra path difference, but sometimes we draw it as a Huygens principle. The ray will go this way. This is your source here. This is your source here. But this source is reflected here. This one is from here. Right? You enter here, go that way, and then come out. Okay, we'll go into more detail. 180 degrees phase change is equal to a path difference of half lambda. That you must remember. Okay, so pi radian equals to half lambda. And that is just extra half lambda, that's all. Okay, let's look at the physics involved. Reflection from a thin film. Remember, this is thin. Right? We have to make it large so they can see, but this is very thin. XA, this is your normal. That's your angle of incident, theta. That's your XA, incident ray. AB is the reflected ray. So these two angle incident and angle reflection is the same. So that is your AB, reflected ray. This is air. This is your thin film. This is air again. T is the thickness of the film. Air thickness there is T. AP is the reflected ray at P. Okay, that is your P here. That's your P. AP is the reflected ray. This is the incident ray. This is the reflected ray. This is the refracted ray. Smaller angle here. And PQ, right? There's a reflection here. So there's your Q. Right? No phase change here because less dense. This denser. Then it comes out. So these two rays will interfere. Come out as your QR. QR. Okay, so this one comes here, reflected surface, reflected, goes there. But this one also come in here, refracted, then reflect at this boundary, firm air boundary, and then refracted again. Okay, let's look at the physics involved now. Path difference. Right? We are looking at the path difference between this one and this one. Okay, we call delta between BA, and QR. Right? Remember, QR have to include this ray there. Okay, path difference. Right? Remember, this is an angle, but it's actually vertical. AP is vertical, PQ is also vertical. Right? This is for this length, these two lengths. And then minus this one. That's a minus half here. Okay, minus half here. Okay, so this one, path difference, T times your N. Right? T, so it's 2T, and times N. N is the reflective index of the medium. Okay, so that's your path difference. Okay, any comments so far? Any comments so far? So for constructive interference, that one there, path difference must be equals to whole number of wavelength. Then simplify, take this one across there. Right? Take the lambda out, so it's m plus half lambda. For disruptive interference, same thing. Right? That's the path difference must be equals to, usually we will look at m equals to 1, half lambda. Okay, we won't bother about higher order. Okay, then we simplify. That half lambda and that half lambda goes off. So we come to NT equals to m lambda. Okay or not? Any comments so far? Anything you need me to explain?
No, sir.
Okay, stop me if you need me to explain. Okay, this is the same formula. For different wavelength, you change this wavelength. That's all. Then you get different color. Same thing here. Different wavelength. Okay, let's look at transmitted light. No change in phase for reflection at P. That one there, reflection at P. No change in phase. Because this is denser to less dense. So this ray, incident, reflected, reflected again, coming out to the eye. Whereas this ray, reflected, no phase change, reflected, right? Same thing, is denser to less dense, reflected, reflected, then refracted. So this ray is that distant, this ray has to travel that distance. The two will interfere. Right? Remember, they are very close to each other. So path difference is just at P, Q, Y, Z minus your PS. Okay. So the path difference, that's the symbol. PQ, that's the extra path PQ, QY. Right? And remember, these two are the same length. They are vertical. Not as an angle that we show you, or think of the angle is very small. So you can think of it as equals to T. What we do? So equals to 2 NT. So for bright fringes, constructive interference, same thing. It must be a whole number, m lambda. For dark fringes, destructive interference must be half. There must be a half there. Same like m lambda, but there must be a half there. M minus half. M equals to 1, 2. Okay, we can compare to refraction. This one and this one. Right? Where this is a formula for constructive interference. It's more or less like for dark fringes. This is destructive interference. Right? For dark fringes, that is your destructive interference. For dark fringes, this is also for destructive interference. So does it all tell you? Opposite to reflection. Transmitted ray and reflected ray are opposite to each other. That means what is reflected is not transmitted. That's all. That's why the two are different. Okay, this one say the same thing. For constructive interference occur for reflected light, there is destructive interference for transmitted light. Okay, so the same light, the same wavelength that is transmitted will have destructive interference. The one that is not transmitted will transmit. The one that is not reflected, sorry, will transmit through. That's what all of these are saying. Okay, non-reflective coating. Non-reflective coating emit more light into the camera and other optical instrument. That's the purpose. The lens in the photo appears blue-violet. Violet. This picture is taken off axis. We don't take it directly. If it's directly, you will see it very dark because there's no reflection. All the ray will enter. But we take it slightly out of the axis, then we can see. These are the they call it blue-violet. Okay, that's another example. On the axis, the lens look dark, which means that little light is being reflected. You can't see reflected light, that's why it looks dark. So most being emitted into the camera. That's all we want. We don't want it to be reflected. We want all the light ray to go into the camera, which in turn is the achieved purpose of non-reflective surface. That's the purpose of non-reflective surface. You allow more light to enter the camera, less is reflected. They make the instrument more sensitive to light. More light enter, more sensitive to light. Okay, so that's your air, that's your glass, that's your non-reflective coating. Usually the reflective index is less than that of glass. That's the purpose. Okay, so cancellation or destructive interference of reflected light ray is utilized to make non-reflective surface. Right? That's why we are using thin film interference for non-reflective coating. Such coating are commonly found on some camera lens or binocular lens and often have a bluish tint. Right? We are just repeating. The coating is put over glass. There's your glass that we want to coat. There's your coating. And the reflective index and the coating material generally has a index of reflection less than glass. That's what we say. Right? This one reflective index is smaller than that. So in this particular case, both reflection at this surface here, there's the incident ray, there's the reflected ray, same by here, refract, refract, and reflect. So there will be a phase change here, a phase change here, from less dense to denser, from less dense to denser. Right? That two part there. And a thin film of, so it means that we will understand this one in a while. Right? There'll be the thickness is a quarter lambda here and a quarter lambda here. So you add this 2/4, it becomes half lambda. Right? Remember, we are looking at normal incidence, even though we cannot show it. Right? We put it at a slight angle. At normal incidence, the path difference between the reflected ray from the coating. Right? This one has to travel T here, reflected back T. That's the path difference. Right? For destructive interference, right? We don't want to see this one. We don't want it to be reflected. So we want destructive interference. So that path difference must equal to lambda over 2. Right? We don't want higher order. We just put it as half lambda. And take the 2 down, that's what we get. Okay, so the thickness is a quarter lambda here, and a quarter lambda there, that's why we get half lambda there. Okay, so you either derive it or you memorize this formula. Any comment? Anything to ask?
No, sir.
Right? N is the reflective index of coating. Okay, we have completed that. So now we are going to let you do your checkpoint. Just remember this formula. Right? All this formula. Okay, one more formula that we have left out, this formula. Okay, try your question. I'm not going to teach you anymore unless we have a bit more time. No point in going too fast with you. Non-reflective 14. Okay, can see? We are now on 23.4. Try this one. Tell me the answer. Number 1. Yep, what's the answer? 1A and B. If you want the formula is just there. That formula, this side. All this formula that we are using, that's all. Turn on the video so I can see that you are doing some work. Turn on the video. Turn on the video. That's right. Good.
Is that a question, Joe?
Question, you are supposed to have your book. Why are you asking me question? You're not prepared for class. Paper must be there, book must be there. Sometimes I want to give out on you. Not interested to study. Right? 23.4.
Difference is larger at B. I mean, difference is larger at B compared to A.
Express, you are told the ray is at normal, near normal incident on a thin film as shown. The reflective indices of the media are indicated. It's indicated here. Express the total optical path difference. I call it path different only. They call it optical path difference, same thing, between the two reflected ray and the thickness D of the film and the wavelength lambda. So they are interested in the path difference between these two. Yep, what is the answer? This is the elementary thing, that's all. There's a path difference. And there's a reflective there. Right? In case you want to look at the note, we are just looking at where we start. If you cannot find your book, it's over here. We are looking at here. We are looking at here. We are looking at here, this part. Okay, what's the answer? Yeah, just using this formula, that's all. Okay, this formula.
Phase change of pi radians, which is equivalent to path difference.
There's a
of pi.
pi, there's a half lambda change here. That one, the extra there. This one travel that distance. Other than that, these two are the same. Okay, this one got extra there. This one travel that distance. That's why there's a subtraction there. What is the answer?
No phase change.
Answer. I didn't say no phase change or what phase change. What is the answer? A value.
2.6 d minus lambda over 2.
Right? That's what we get. This 2dn because of here. 2d, d down, d up, and times the reflective index. Then there's a phase change here. That's why we have to subtract that. Then put in your value for your reflective index, half lambda. That's the answer. 2.6 d minus half lambda. Okay, what's the answer for B? Same, do the same principle. Just trying to force you to do what I've just teach you. Yep, what is the answer? Remember, there's a phase change at these two places, this place and this place. There's a half lambda there. Yeah, what's the answer?
2.6 d.
2.1.
6d.
2.6 d. Let's see. Right. The half lambda, I can forget about them because both of them will eliminate each other. Right? Can put it in there. Right? Remember, a phase change of pi radian occur at the reflection here and here. So in this case, it's the same. Right? That 2d, d down, d up, times 2 times n. And then there's a half lambda here. That's why we add. There's a half lambda here. That's why we subtract. So that two eliminate each other. Okay, 2.6d. Okay, good. Right, number 2. Identify your lambda, identify your n, and then what formula you are using. You are just using this formula.
2 mu t minus lambda over 2. 2 nt minus lambda over 2.
There should be an answer there. Since they have given you n and lambda, there must be an answer. We are using these two formula. This formula.
338 times 10 to the power -9 meter.
Okay. For constructive interference, right? We just usually won't bother about higher order. We just put our m equals 1 and 2d times 1.33. Right? That half lambda, you take across there becomes half lambda, that's all. So your lambda, sorry, this one take over becomes 3 over 2 lambda. Lambda is 600 times 10 to the power -9. Okay, 0.338 micrometer. How about destructive interference? Just forcing you to use a formula to know which formula to use as well.
2 mu t 2 and 2 dn minus pi over 2 equals to pi over 2.
What's the answer?
226 times 10 to the power -9 meter.
Right, same formula there. You must know how to derive it. Right? No point to memorize all the formula, a lot of formula to memorize. Go to the basic one. This is for destructive interference. Right? To under M. Minus and minus will go off. So take your M equals to 1. So it's 2dn, n is there. Then this becomes your lambda. This is your lambda. Okay, 0.226 micrometer. Try number 3. Right? Always have a picture in mind, either sketch it roughly to know what is happening so that you can imagine, either in your head or on the paper. Surface of lens is to be coated with a translucent material of refractive index 1.35, so the light of wavelength 100 meter will not be reflected. Calculate the minimum thickness of the coating. Right? Roughly have a picture. That's your coating. That's your coating. That's your lens. That's your air. That's your incident ray. Okay, what's the minimum thickness? You can memorize the formula if you want to, or work it out. You should be able to calculate the optical path. You want destructive interference, so it's half lambda. Okay, what's the answer?
×10⁻93 meter.
93. Where the wavelength is not reflected, it must be transmitted. So for dark fringes, okay, don't need to go too far. Just put it as half lambda, good enough already, because you are interested in m equals to 1. Right? Or as I say, you want to memorize the formula, that is the formula. If not, that is your t. It's going to go back, that's why you got 2t then times your n, that is n as well. Then that it is half lambda, that's why you get quarter, and put in your value. 92.6 nanometer. Must remember there must be a unit there. I use nanometer, I get nanometer. Okay, did you get correctly or not?
Yeah,
Good. Number 4, sorry, finish already. So we can go to the next one. We'll go is 23.5. Okay, let us
topic.
carry on with another topic. We won't be able to do much, but I can try to do something. Just a start. You cannot see, let me know. Don't keep quiet.
Okay.
Okay, let's go to review your self-test. Fill in the blank. When light, like this in your worksheet, number 27. When light is incident from a less dense medium to a denser medium, there is a what? 0 phase change, or pi phase change, or half pi phase change. Just review you. These are essential things that you must remember. Yep. Why it takes so long?
Hi.
Good. 5 radian, 180 degrees. For reflection from thin film at normal incident, what are the conditions for constructive interference and destructive interference? What's the formula?
What is that? The one equals to lambda
Go to the basic.
equals to lambda meter. Yeah.
Go to the basic, that's all. You should be able to get the path different there. And then m half lambda.
That's for the destructive.
And destructive, either you get it or you memorize the formula. It's best to not memorize. Go to the original way how you get it. Right? This is memory work already. But anyway, this is the answer.
Sure.
Yeah.
But the dark fringes one is the constructive, right?
Dark fringes is destructive.
But because this one got half lambda for the bright fringes. But
we are going to this stage there, that's all. Right? We are going to this stage there. This one. Go and derive it. Go and derive it. That's why we get the path different. And for constructive, this one equals to m lambda. And then you can simplify it. That's what we get. And for destructive, same thing. Right? That's what we get. And then there's a formula for destructive. Then simplify it. I cook for you this answer, that's all, and this answer. Either you memorize the answer or go to a basic principle. Go to that. It doesn't take a long time. Okay or not?
okay.
Right. The other one is transmitted ray. Sorry. The other one is transmitter is just opposite to this one, that's all. I mean, this one becomes your bright, then this one will go down to your darkness, that's all. That will change the negative sign. Okay, a glass of a camera is to be coated with a non-reflective coating or reflective index, and the coating is to prevent the reflection of light of wavelength lambda. What's the minimum thickness of the coating? Right? This is just a memory formula. Either you memorize it or you derive it. Doesn't take a long time. What's the answer? Yeah. You just use the formula previously in calculating. That's all. This formula. Thickness is lambda over 4n. Okay. You can start doing some of the focus question so that you force in on all this formula that we have derived for you. If not, you forget it. That's how you help yourself. Right? Nobody can help you. You are your own person. How well you need to do is depend on how much effort you want to put in. Okay, let's go to diffraction by a single slit. Right, this is the picture. Show you the diffraction. Right, page 172. Syllabus. Explain diffraction pattern for single slit. Use the formula for the first minimum. We want only first minimum. We're not interested in higher order in the diffraction for single slit. They say use only, they didn't ask you to derive. Right? But anyway, we derive for you. Use the formula, that one, as the resolving power of aperture. So it's the same thing. Both of them the same formula. Use the formula for resolving power of aperture. Okay, let's go to review diffraction. Is the spreading of wave into the geometrical shadow as it passes through a slit or obstacle. Okay, that's your slit. That's your slit, right? If you imagine that is your light passing through straight line, then this is your shadow, this part. despite your shadow. Or if this is an obstacle, that's your light. You think of light as travel in a straight line, then this is a region of shadow. Right? But reflection say it's spread out. That's why we are seeing. Instead of going straight, it is spreading out to the region of shadow. Right? So we can call this one gap or slit. And then we give a symbol, size of aperture, A. Okay? So that will be your refraction over an optical. That's your STPM work. Memorize the term diffraction. Your worksheet should be for you to write down. You can write down. The experiment. That's your slit. These are optical. These are optical, or this is your gap. This is your straight edge to produce your plane wave. This is your power supply, and that's your lamp. Do in a dark room. This is your paper or screen. Represent using straight edge to produce plane wave and wide side gap between obstacles, so we can adjust that gap there, narrow or wide. Wide gap means aperture size is very much greater than your wavelength. Okay, so that, as I said, this is called the region of shadow. Region of shadow. So how do we draw that? Yeah, that's the experimental result. So we can draw that. Sorry, press the wrong button. Okay, so that's how we draw. It's still plane wave here, but it's spread out to the side, spread out to the side. Okay, it's plane wave. It's still plane wave, except it's spreading to the side. That's all. That's why it's standing. That means it's bending, bending at the edges there. Wavelength and frequency still the same. The speed still the same. It doesn't change. Right? Going through the slit or aperture doesn't change the wavelength or the speed. It's still the same wavelength. Then when we say narrow, usually we say that aperture size is very close to your lambda. Okay, so now plane wave, we get circular wave or three-dimensional spherical wave. Right? So we can think of narrow slit as a point source. And we can use Huygens principle to draw the graph. Right? To sketch the diagram. The gap is about the size of wavelength in this case. Emerging rays are circular. These are circular waves. The wave has spread into the region of shadow. That's the region of shadow. That's the region of shadow. Okay, so we can compare small gap, narrow gap to large gap. This one spreading more. If it's the same as the wavelength, then you can see it's 180 degrees. Wavelength of incident and reflected ray are the same. Wavelength hasn't changed. Amount of diffraction. This one shows you the amount of diffraction. This is more diffraction. This is less diffraction. Depend on the aperture. Diffraction across an optical, example, a hill. This can be an optical. That can be a hill. This can be long wavelength. Long wavelength, there's more spreading. The wavelength of wave is shorter. The spreading effect, or we call diffraction, is much smaller as well. Like this case, short wavelength, spreading is not that much. Where we can apply to real case television waves. Short wavelength, no much diffraction. Long wavelength radio wave diffraction. There's a house there. The house can listen to the radio signal, can receive the radio signal, but cannot receive the house here cannot receive the television wave because short wavelength. Okay, so that's why it's happening. For long wavelength radio wave, there's a lot of spreading or bending or diffraction. then the house can receive the radio signal and listen to radio. Where television tend to have shorter wavelength, so less spreading. So the house here cannot receive the signal at all. Blocked by that, right? Same. Sometimes a large building may block your house, so you may not receive any signal from television. Okay. Experiment. Now you can use pen light laser or less laser pen. There's your single slit. Single slit. That's your retort stand. That's your clamp. And that's why we observe on the wall. You try on the piece of paper, fold it up there. That's what we see. There's your slit. So we are interested in this. That's all. There are other less bright one around there, but we are not interested in that. Interested in the center one, which is the largest there, and then these two smaller. Right? That's the slit. Diffraction is on this side, not on the top there, right? Not on the vertical side. Sorry, not on this length there, but on this horizontal side there. Diffraction is on the horizontal side. Right? It's horizontal side, not this vertical side. Some vertical still the same. Okay, as I said, we can use your laser pen. It can be obtained very easily and cheaply. To obtain the plane wave from point source, right? You can get it from textbook, but sometimes you have to be careful, have to use your head a little bit. Monochromatic light is correct. How do you get a plane wave from a light source? There's your STPM work. How to get a plane wave from a light source? Can you remember? Yep, can remember or not? Right? Monochromatic light gives spherical waves. Right? That's correct. So we want it to be plane wave. So we have to put a convex lens there. And that distance between the center here of the lens and the light source must be a focal length away. Then we have plane wave. Okay. You want plane wave here and fall on the slit. Convex lens is at a focal length F from the source. Right? Source is the light emitting source. So that the wave emitted from the lens are plane waves. That's the result. If you use a laser, right? There's the intensity. Right? Let's do some observation. There's the center of the slit. You draw a line there. The center will be the largest one. Right? Maximum. Others one will be smaller. And then that will be a dark. Right? Instead of dark line, we say dark band. Because of our threshold of vision. Okay, so there's a central line. There's your theta. This is also theta, the same. Right? Theta at the center there. At the center there. Diffraction pattern. Central maximum bright band of width greater than the width of the slit. That's the width of the slit. That one is greater. Right? How wide will depend on that width of the slit. The width depends on the size aperture. Right? That width there depend on that aperture size. Being greater, if this is smaller, this will be greater. Light spread through an angle theta on both sides. That's the angle theta on both sides. Right? To the dark band. So usually we measure at the center there. Angle is at the center there. Angle theta is given by sine theta equals to lambda over A. That you have to memorize. No choice. A is the width of the aperture. Think of the picture. Center maximum is where most of the light intensity is concentrated. Maximum occur at theta equals to 0. Yeah, at this point, that's the maximum intensity. Right? This is the first one. Second one and third one. Right? Decreases considerably. That means the largest intensity is here. Usually we won't bother about the first and second or third maximum because intensity is very low, much lower. Right? I think this is about 80%. This one is less than that. Width of fringes in the diffraction pattern are never equal. Not like your interference pattern for Young's double slit, where this is the same, right? The fringe separation of fringe width is the same, but this one no. This one is larger. This one is smaller, and then smaller and smaller still. Right? This is the largest. In case of diffraction, the distance between the bright and dark band gradually decreases. Right? That distance becomes smaller and smaller also. Intensity of the bright diffracted band never remains the same. They are not all the same. Right? This is smaller, not like interference pattern for Young double slit. All the intensity is the same. Remember that. Right? Intensity is maximum at the central band. There's a central band, maximum there, and decreases on either side. Decreases on this side. Decreases on that side there. Right? Intensity decreases. You can see there, smaller. Right? You can use Eugen's principle. That slit there, you can redraw that. And then remember the slit is wide, so there are many point sources. This one draw for you a few only, but there are in between there are others. So each point there, there's your wavelet. Each point there can draw your wavelet, and you can draw the next one. But of course, this side there will tend to curve lah. As plane wave fall on the slit, points on the wavefront at the slit act as secondary point sources emitting spherical wavelet. Right? These are your that slit there, your plane wave. These are your secondary point source. Secondary point source. It emits secondary wavelet. That's all. So where we see our dark bright band there, we have constructive interference. We see this dark band there, destructive interference. Right? In between, they will have different amount of constructive interference. I mean, the graph is only maximum at the constructive interference there. After that, it will decrease. Intensity will decrease. Okay, this just try to express the same thing using Huygens principle. Right? These are all the spherical wave that is given out, and we can see that the wave blood from each of these points will meet at this point. That's why we get a dark band there for constructive interference. Okay, as I say, this is not required. Right, I better make a note there. Sorry. What's happening? Right? Not mentioning in syllabus how to derive, but as I say, just for your curiosity, in case you are, but you don't need to go and study that. Right? I just put a note there. Right? No point in study, just understand it. Why you get how you get the formula. That's all. You don't need to go and know how to derive it because it's not mentioned in syllabus. Don't waste your time on that. Okay, let's go to roughly how you derive it. Right? Usually we use rectangular slit, so we call it Fraunhofer diffraction. Right? You're interested in this one? A slit width. So we divide the two half. Right? That's your B. This half and that half there. Or we can redraw that. Right? This half A, that's half A. That's still your P. That's your Y. Okay. So that's your N. I call it C here. Sorry, C is different. C is down here. This one is N here. Ray traveling towards the first minimum at P, make an angle of theta. So this angle is theta. This angle is theta. And center there, that's the angle theta. This angle also theta. They are very small, right? Because it's quite far away. This slit is quite small compared to distance. So that angle and that angle is almost the same, right? Very small. We put it as equal. So we are interested in rays traveling towards the first minimum. That's your P minimum. Make an angle of theta. That's the angle theta. Right? So this angle theta. Yeah, we are looking at destructive, not constructive. Destructive interference occur between the rays from points A and B on the wavefront. Right? You can see the wave coming from A and wave coming from B who destroy each other here. That's why we get the minimum. Right? So the path different is that extra path that this one had to travel from B to P and A to P. That extra path had to travel. That's called your path difference. Bn is half lambda. And in triangle, right, this triangle A and B, right, you can just redraw that here. The angle is theta, is half A, half A. This path difference of lambda over 2. Right? As I say, we are not interested in higher order. We are interested in the first destructive band, that's all. And from this triangle, sine of this angle, this is 90. Right? This is 90. Right? We are looking at this triangle. It's 90. So sine theta is just this one over there. There. And the half times 2 here, times 2 here, we get rid of the half. We got lambda over A. Okay, so far? Okay, so point A and point B are secondary point. They will destroy each other at P. We can also look at a point just below A, a point just below B. They still have the same, they will still destroy each other. Our difference is half lambda. Right? So we can also think of others also, other points there below A and other point below A, corresponding point. They will destroy each other. Okay, so we are interested up to the first maxima. That's the central maxima. Okay? Central bright fringe, first bright fringe, first bright fringe. This is in terms of, right, the distance is in x-axis is sine theta. So this lambda A, this minus lambda A. Angular width of the central bright fringe, right? There's the angular width, the one there. So it's 2 theta. Right? If you want to look at the picture, that's what we look at lah. This one, this is theta, this theta. So angular width of this one is 2 theta. Theta plus theta is 2 theta. Okay, that's why we get our 2 theta. Right? Let's look at this formula. For A equals to lambda, right? Theta is 90 degrees. Theta equals to 1. Theta equals to 1. So if you draw this graph, it is more like horizontal. That's why we have uniform intensity, right? That's Young double slit. For A very much greater than lambda, right? This one very much greater than this one. Theta is very small. Right? Example, where A equals to 2 lambda, twice the wavelength. Then we put your 2 lambda here. This becomes half or 0.5, so it's 30 degrees. Okay, so that's just to review with you. If equals to lambda, is 180 degrees. Diffraction, if very much great, A very much greater than lambda, only slight diffraction. This one is also just show you slight diffraction. This literally is plane wave. Only where it's small compared to wavelength, then it's spherical. Okay, resolving power. In dark, as the car moves away from the observer will see two rare light separate. Now you can think of these two rare light of the car. As you move away, initially you see the two rare light, two bright light there. After that, if far away, you will see almost. Right? Here you can still see them if you lower the intensity of the graph. But here, too far away already, you can't see anymore. Right? Can't see anymore. We just see as one light source only. As the car moves further, the separation between the two rare light, these are the two rare light, get smaller and smaller, right? The separation gets smaller and smaller until it becomes one. Until the eyes are not able to distinguish. This is not able to distinguish. This one we can still distinguish. This is due to diffraction of light as it passes through aperture of the pupil of the eye. Right? So application, we can use telescope to see distant objects. Resolving power optical instrument, as an example, microscope or telescope, is the ability to distinguish between objects that are close to each other. Here we can distinguish, we can see as two objects. Here we can see fully well resolved. This one cannot. Right? The two objects becomes one, so it's not resolved. So we have what we call Rayleigh's criterion. States that for images to be just resolved, the central maximum of one image must fall on the first minimum of the other image. That image, there's the intensity graph. This is the minimum. So Rayleigh criterion is just this is resolved as long as this maximum and this minimum coincide, or it can be the same. Right? Maximum of this one and minimum of this one coincide. That's what this is saying. Okay, so we call that minimum determined subtend by the source equals to the angular separation between the central maximum and the first minimum. Here's the same formula, resolving power, same formula as for diffraction, destructive interference formula. Right? Lambda is the wavelength. This is the width of aperture, usually can be the pupil of our eye, or it can be the lens of the telescope, right? Eyepiece of telescope. And usually we make our A very large. Then this theta mean is very small, right? Very small. So in this case, we can make approximation. Sin theta equals to theta mean equals to lambda over A. Okay, that is a criteria. Theta mean is measured in radian. This is for rectangular aperture. Right? For circular aperture, we have to multiply by 1.22. Right? This one is not mentioned in syllabus, but as I say, we are not sure, so we have to teach a little bit extra. So for circular aperture, same thing. Right? You just multiply by 1.22. Okay, so usually we are going to observe a distant object. This is our telescope or eye. This is a theta mean. This is your D, or it can be radius. So we will use this formula. Arc length, treat this as radius. Right? Here's your radius, R. That's your theta mean or theta. That's your S. Think of it as a circle, circular arc. Okay? And there's a formula that we'll be using. Okay, so we have completed. These are all the formulas. Let's try some questions before we call it a day. So you can do the rest yourself at home to reinforce what I've learned from you. Okay, number 30. Which diagram of a ripple tank experiment shows the appearance of plane wave passing through a white slit? White gap, sorry, white gap. What's the answer? Yep, what's the answer?
A, teacher.
No, A is for narrow gap. Donkey, wavelength must still be the same. This one looks like wavelength is increased already. Right? Wavelength does not change. This one, the wavelength changed. A is for small gap, but the wavelength shouldn't change. Okay, what's diffraction? Right, you got your worksheet, you can write it down. In fact, you should be writing it down as I teach you already. That's the problem with you is you don't bother to bring your worksheet. And then you are not going to study at all. You're wasting your parents' money. That's why I have to scold you every time. Right? It's the spreading of wavefront into the geometrical shadow as it passes through a slit or an optical. For light wavelength lambda passing through a slit or width A, the first dark fringe occur at theta. So what is the formula? Yep, what's the formula? Yep. State the relationship. Okay, that's the relationship. That's a relationship. State Rayleigh's criterion for resolving of the image. Okay, see where you can state for me, or you can look into your book. Yeah, state Rayleigh's criterion for resolving of image.
It specifies the minimum separation between two light sources that may be resolved into distinct objects.
States that for images to be just resolved, the central maximum of one image falls on the first minimum of the other image. That's all. Memorize it. State the resolving power of a telescope of slit width A or wavelength lambda. Yeah, same formula. Nothing there. That's all. Okay. Let us try one or two questions before we stop. Okay, number one. Have a picture what you are doing. A picture there so that you know what is going on. Either you draw it or you have it in your mind. A narrow slit of width A is illuminated normally by a monochromatic light of wavelength lambda. Calculate the angular separation between the first minima on either side of the diffraction pattern when A equals to 2 lambda. That is your angular separation. 2 theta. Yep, what's your answer? Yep. What's the answer? Can or not? That's all. Use this formula. Find your theta. Right? Put your value 2 lambda inside. Lambda and lambda cancel is 30 degrees or pi over 6 radian. The angular separation is 30 plus 30 is 60, or pi 6 plus pi 6 is pi over 3 radian. Okay, try the other one. B, what's the answer for B? Yeah, what's the answer for B? Same calculation, that's all. Same like what I just did for you. You just calculate it yourself. Instead of 2 lambda, you put 4 lambda, that's all. So what's the answer? Yep. Why take so long?
$60.
Right, same formula. Put 4 lambda cancel. Sorry. All right. So it's a quarter. A quarter, then you can convert it. And use your calculator to calculate out for you. 1/4, what's the angle? Angle is 14.5. And then you double it. Angle separation is double that. This one is theta. This one is theta. That's why you times 2, 29 degrees. Okay, copy whatever you want to copy. You can either use radian or remember the conversion factor. That's your degree, that's your radian. Okay, we've completed try number 2. Then we'll call it a day. The rest you can try at home. So tomorrow I see you again at 10 o'clock.
Yeah, sir.
Monochromatic light of 470 nanometer is at normal incidence on a narrow slit. A screen is placed at a distance of 50 cm from the slit. The width of the central maximum is 3.8 millimeter. Find the width of the slit. Okay, you have to find A. Right, draw a rough picture so they can understand what's happening. Right, there's a rough picture. And then identify your term. That's your lambda. That's your D, that distance, D. That's your Y. Right? That's your S. So Y is equals to 2S. Okay. What's the value for A? I've already identified for you all the terms already. Now you are supposed to choose the formula and work it out. Yep. What's the answer? Yeah, you have to use this as arc length is R times theta. In this case, your theta is still the same theta. Your R becomes your D. That's your S. Okay, calculate your S first. Sorry, calculate your theta, this angle theta first. Theta is S over R. That's your S. That's your R. Think of it as the arc out of a circle, because this is quite far away. And calculate out. Okay, you have to divide this by 2. Because S here and S here. Now divide this by 2. Use the same unit, and yeah, all right, it's cm. So convert this to cm. Divide by 2. Okay. What's your A? Then apply a formula for diffraction formula. Okay, now what's the answer? Yeah, that formula.
Wait. 7.08 times 10 to the power of -3 meter.
Oh, what? Where did you go wrong?
Oh, the 470 I times with 10 to the power of -9.
This one I use nanometer,
Yeah.
and your
I wanted to use meter.
theta. That's your theta.
Yeah.
Theta.
Oh, sorry. I put divide sign 0.0038. I never put 0.0038. I put sign in.
Have to be careful. Cannot be careless. Use unnecessary mark.
Now I got it.
Right? Theta is in radian. Okay. Anything to ask? I will stop today. The rest you can try at home, and then tomorrow we will go over the answer.
Yeah, tomorrow.
Make sure you put the effort. I can't learn for you. I'm the one learning so far. Teaching you a lot of things. This is new to me. Right? I don't teach in A level. I'm learning also. That's why I'm learning all my STPM again. So make sure you want to force it in, you have to try the question. No shortcut. If not, you forget everything. It's just like your teacher asking you to practice vocabulary. You can memorize the meaning, but I don't know how to use it. No point. That's what is happening now. You memorize all your formula, but I don't know how to use it. So you don't know which one to use. Okay. Anything you want to ask? If not, we will stop here.
I can stop here. Okay, thank you.
Okay. We'll see you tomorrow then.
See you tomorrow. Bye, Jay.
Okay, bye-bye.